All right, guys, so this is going to be our next little bit for our astrophysics unit. I wanted to take a few minutes just to review the life of a star. Okay, we're going to talk about one the size of the sun, which we've done before. We've kind of talked about that in previous videos. However, I'm also going to talk about after that what happens if the star is significantly larger. All right, so we're going to go ahead and look at that now. So first we start in whatever situation we start out as a protostar. Remember, protostar is where we've got the gravitational potential energy of those atoms in the nebula or whatever it is, that as they pull together they start to lose gravitational potential energy, which turns into kinetic energy. Of course, kinetic energy is proportional to temperature. As the temperature goes up, we're then able to start fusing hydrogen into helium. So that's what happens. We create the main sequence star in which hydrogen is fusing into helium. Okay, now if we have a main sequence star with hydrogen fusing into helium, the next step is that eventually the hydrogen gets to a point where it cannot fuse as much anymore, right? When the hydrogen starts to get to the end of its cycle, what happens is that some of the stuff on the outside, and we talked about the photosphere, but some of that other gas kind of floats to the outside, and that's where we kind of get this red giant as the star is starting to cool off and beginning to die, that the stuff on the outside is kind of getting away a little bit. Okay, now what happens after a little while is that because it's cooling off, the stuff in the middle doesn't have that heat degeneracy pressure anymore, right? It starts to actually be pulled inside because gravity is greater than the heat degeneracy pressure. And so as it starts to fall in, we then have a helium flash, which is where the the helium now starts turning into larger atoms like carbon and other things like that. And so now we have basically a helium burning star. It's still pretty large, and so it's probably still classified up in that red giant area, but it may be more of a yellow giant or something at this point. As it continues to burn, the same thing that happened to the hydrogen fusing here, in which the stuff on the outside starts to kind of float away. It starts to cool off a little bit. So you've got hydrogen burning on the outside, you've got helium burning on the inside, and so that is happening all at the same time, but it is starting to again become this large giant. As it starts to cool off, as the stuff in the middle stops to fuse quite as much, the material on the outside will continue to kind of float away on that radiation pressure. It's not burning, it's not fusing anymore, so it just kind of floats away, giving us a planetary nebula. And at the center, we're left with the core of the star. The core of that star will usually be fairly dense. It'll be very, very hot, therefore very, very bright, and it will be a white dwarf for a specific amount of time until it cools off, and it will cool off over thousands, billions of years until it becomes what we call a brown dwarf because it's no longer hot. All right. Let's look then at a large star. Okay, now when we see a large star, we're talking about significantly larger, maybe 8 to 10 times as large as the sun, or bigger, right? We're talking about mass here, so a significantly larger star. Again, it's going to start as a protostar, right? Now, as it burns, it's actually going to be blue instead of yellow, right? The sun size was yellow. Why? See if you can remember why this one's going to be blue. I'll give you a minute to try to remember. All right, so hopefully you remember that higher mass means more gravity. More gravity means that there's going to be a larger force pulling all those particles in the middle. In order for the star not to collapse, it's going to, as it decreases the potential energy into kinetic energy, again, it's going to heat up more and more and more, which is going to give you that radiation pressure, that heat radiation pressure pushing out to balance that gravitational force. It has to be that way so that there's hydrostatic equilibrium. Otherwise, the star would completely collapse under gravity. So therefore, we know that it gets up to a higher temperature. Higher temperatures, remember, temperature is proportional to or inversely proportional to the wavelength, which we learned in Wien's law in the previous videos. And so therefore, as the temperature goes up, the wavelength got to go down, the frequency is higher, therefore we're getting some more blue instead of yellow. All right, so same thing is going to happen as did with the other one. As the center starts to run out of hydrogen, it doesn't completely run out. It's just getting to a point where there's not enough hydrogen to sustain the fusion. Then we get the red supergiant as the outside starts to kind of burn and pass away. At this point, it is going to undergo the helium flash and start burning again. Again, it is a larger star. There's more helium than there was in the low mass star. And so we do have, again, it'll probably be a bluer supergiant here. Okay, as time progresses, it turns into a multiple shell burning supergiant. Now, the reason why we say multiple shell is because we've got hydrogen still going on the outside here, right? Then you've got helium on the inside of that. As you get deeper, depending on the size, you are going to get larger and larger atoms that are burning and fusing inside of the star. Those are happening in shells, right? Not clearly defined shells, but on the outside you're definitely getting more helium fusing. The helium is next, and the more dense the atom is, the closer it's going to be to the center, the deeper it's going to drop. Just like denser things tend to drop to the bottom of a box or a container here on Earth. You shake it around, light things are going to go up to the top and heavy things are going to sink down to the bottom. So that's basically what's happening inside of the star. The heavy elements go to the middle and they're burning and fusing in these shells. All right, next we turn into a supernova. Now, why does a supernova happen? Well, the supernova happens when we can't fuse anymore, right? The fusion basically has stopped, right? There's not enough heat radiation to push out as there is gravity pulling in. So therefore, what's going to happen, and we'll talk about this a little bit more, is that all of these atoms, because there's no more heat radiation pressure, are going to collapse into a neutron star in the middle. Okay? Now, when all of those atoms collapse into a neutron star, it's now going to be as dense as the nucleus of an atom. Okay? Which means all of this space that it used to take up, it's now in a very small space. The same mass, it's just packed into this very small space in the middle. So everything else on the outside is going to have a very large gravitational force towards the middle, and anything that doesn't fuse into this neutron star is going to fall in and explode out, and that's what's giving us the supernova. Right? Now, in the end, the supernova is going to be gone, and all that's going to be left is the neutron star or black hole with your supernova material and the nebula on the outside. Okay, so we'll talk about very, very soon that idea of neutron star versus black hole. Okay, before we do that though, I want to make sure that we've got this idea, because you do have to draw this from time to time. What does a solar mass star look like on the HR diagram? Well, we start here, okay? We move up as we turn into a red giant, right? As it starts to cool off and expand, okay? Somewhere in that time, the hydrogen starts fusing into helium, which gives us the helium flash, which then brings it to here. Over time again, it starts to expand. It starts to get hotter as all of the stars starts to collapse into the center. It's getting really, really hot, which is where the outside then kind of fades away. That's the planetary nebula ejected. And then it goes down. This part is not super specific, but it does then go down to a white dwarf where it's not very bright anymore, but it is very hot until over time it cools off, until over time it cools off. All right? Now, I want you to look at this picture here. Yes, it says Chandrasekhar limit, but I want you to look at this picture here and see if you can remember what this means, this Feynman diagram, right? What do we have here at the bottom? Up, down, down. Hopefully you remember that being a neutron. Okay, up, down, up. That is a proton. And then of course here you've got your electron and your electron neutrino, right? This is a neutron that is down here at the bottom. As time progresses, it's going to release your W- boson, okay? Which then takes away that negative charge, turning a neutral into a positive, right? And then we create the electron and the electron neutrino, right? This is an example of a weak interaction, okay? The neutron is turning into a proton and electron. What's happening inside of a very, very large star is actually the opposite. We're taking this star, right, which was fusing all sorts of elements, okay, and it's so large, even after emitting that planetary nebula, after all that stuff leaves, all that extra mass, the core of the star, which for a solar mass star becomes a white dwarf, but if that white dwarf is too big, if the white dwarf is more than 1.4 times the size of our sun, then that white dwarf, the gravity there is so great, it's pulling those atoms together, right? Now atoms, remember, are made up of a nucleus and then little electrons around the outside, right? A nucleus, and then nucleus meaning protons and neutrons, and it's got little electrons on the outside. But when gravity gets so strong that it's pulling these together, there's a problem. These electrons don't like to be in the same place. And if these atoms are overlapping at all, then that means that the electrons are allowed to share that same place. Now that's a problem. There's something called the Pauli exclusion principle, right? Which basically says that electrons aren't supposed to share the same space, okay? And that's a problem. And so the atoms, rather than allow themselves to share the same electron space, they go through this process right here backwards. They go through this beta minus decay, except instead of creating the beta minus, they're actually taking the electron and the proton and putting them back together again, so that I no longer have a whole atom with a nucleus and electrons, but the electrons all combine with the protons, which means that I just have a whole bunch of neutrons there, which means I now have a whole bunch of extra space that gravity can now bring these things in together. Okay, of course, now all that I have left is neutrons. The neutrons aren't repelling each other, so they can actually come in together. And my neutron star is going to have the density of a nucleus, right? Nucleus. I'm sure I can spell it correctly. All right, so now, instead of being a white dwarf, all the protons and electrons have collapsed into neutrons, and we now have a nucleus, a neutron star that is only made up of neutrons. Hugely dense, right? But no charges, no repels, so those neutrons are just packed in there. That's what happens when the core of my star, or the white dwarf, the remaining white dwarf, is more than 1.4 times that of the sun. Now remember, this is after we've let off all of that extra stuff out there. This is an important number. You should memorize this. You need to know that, and you need to know the name Chandrasekhar limit. All right? Now, continue. This is a supernova, right? Now this is really cool, because what's happening here is we've had a star that's blown up, right, and has let off some stuff. This stuff is now close to a star, and so some of this can actually be pulled into that new star, right? And so we're going to get some of that pulled in. This right here is a supernova, right? At the center, huge amounts of energy, but at the center you're either going to have a neutron star, or you're going to have the next step, which we'll talk about in just 1 minute. So the next thing we need to talk about is exactly that, the Oppenheimer-Volkoff limit. And yes, you do need to know this term. Okay, so if we get over 3 solar masses, right? Again, we're talking about the white dwarf. Okay, that white dwarf, if it's over 1.5, then it turns into a neutron star, right? Now, if it's too big, if it's more than 3 solar masses, what happens is that neutron star overcomes what's called the neutron degeneracy pressure. Okay. Now, one thing I forgot to mention is that when we have those protons and electrons, right, what's keeping those atoms separate is something called electron degeneracy pressure. Okay, this is an important term. You need to know this term, electron degeneracy pressure. When we overcome the electron degeneracy pressure, that's when the protons and electrons get pushed in together to become only neutrons and become a neutron star. If it's so big, still 3 solar masses, if it's so big that gravity continues to cram those neutrons together, well, you know what? Those neutrons, they don't like being in the same place as each other either, right? If you pull so hard that these neutrons start to be pushed together and start to overlap or combine, then the neutrons give up. The neutron degeneracy pressure is overcome. The neutron degeneracy pressure is what allows them to hold their place and to stay as neutrons. But if you push hard enough, even the neutron degeneracy pressure is going to be overcome. And at that point, we create a black hole. A black hole is what happens when those neutrons all get sucked in together. They get pushed so hard that even the neutrons themselves cannot withstand the pressure. Now, of course, what that means is that we have a huge amount of mass in a single point, okay? That single point now has a huge amount of mass. The gravity of that singularity, that single point, the gravity of that is so great that not even light can escape it. When you look at it, any light that gets past a certain point gets sucked in. That's why it's black. It's black because we cannot see it. We can't see it because there's no light that can reflect off of it and bounce back to us. That's how we see things, right? We see an apple, we see the desk, we see ourselves in the mirror because light is shining off, bouncing, reflecting off of something and entering our eyes. If that doesn't happen, if none of the light can escape to come back to us, we can't see it. And therefore, it's a black hole, okay? So how do we know they're there? Well, we know they're there because of the huge amounts of gravity that's present. Even though we can't see it, there's so much gravity there, we say, you know what, there's got to be something. There's got to be something there, and based off of all our other understandings of these things, is we say, okay, well, based off of what we know, this could be a star that overcame its electron degeneracy pressure to become a neutron star, that overcame its neutron degeneracy pressure to become this other thing, and all the mass doesn't even allow light to escape, and therefore we can't see it. Now, you may have noticed last year, about this time last year, that it was really awesome because we were talking about this in class. They came out with some photos of a black hole at the center of a galaxy. Go search it on the web. It's really, really neat. All right. Now, another thing that happens is as particles get close to a black hole, as this particle gets really, really close, it starts moving faster, right? It goes faster and faster and faster. And remember that kinetic energy is proportional to temperature. So if that particle has a huge kinetic energy because it's getting closer and closer and closer to the black hole and going faster and faster as it gets closer and closer, the temperature's got to go up. Now, if the temperature goes up, what's going to happen? Well, remember, temperature has a relationship with wavelength and with frequency. If the temperature goes up, the wavelength has to be lower, so low that what we see, if we see anything before it passes that, what we call event horizon, where we can't see anything anymore, we do get very low wavelength electromagnetic waves. Very low wavelengths would be very high frequency, which would be possibly X-rays. And so when we look at something black, when we look at something where we can't see it out in space, but we know there's a huge mass there, if we can see X-rays being shot out by particles that are getting close to it, then we say, yes, those particles have to be accelerating so that they're so fast to have such a high temperature that they are emitting those X-rays because of what we talked about with Wien's law. All right? So really, really neat stuff. Okay? Now, one last thing that I want to talk about before our last page is stars are spiraling around the galaxy. Why would they be spiraling around the galaxy? What is the centripetal force? There has to be a force that causes them to go in a circle, a force pointing towards the middle. Well, as we have hypothesized and as we kind of have proven based off of the pictures that came out last year, is that at the center of the galaxy, there is a black hole. There's a supermassive black hole, a black hole that has so much mass that it affects even stars that are light years and light years away, so that they have enough gravity that they can continue in a spiral around the center of the galaxy. And that, my friends, really, really cool. All right, so I'm gonna give you a minute. What I would like for you to do is work through A, B, C, and D here. I want you to think through the answers to those. When I ask you to pause the video, please do it, because then in the next couple of seconds, I'm gonna show you the answers and we'll talk through it, and then we'll be done with this video, all right? So, here we go. Pause the video. All right, here we go, let's wrap it up. So, state the condition necessary for the sun to move from S. Well, remember that is when most of the helium, not all of it, but when most of the hydrogen has fused into helium, then that's when we start to move away. Remember, we do still have hydrogen on the outside, in those outer shells, but most of the hydrogen has been fused to helium, and so that's what then allows us to move into this giant region. Okay. Next says, state and explain the change in luminosity of the sun between S and I. Well, you can see on the graph over here that the luminosity is going to increase. The reason why the luminosity is increasing is, of course, because the surface area is increasing. The temperature is actually going down, so it actually does require a significant increase in the surface area. And we saw that picture of a supergiant versus the solar system, right? So it's a huge increase in the surface area of that star. Okay, letter C, explain by reference to the Chandrasekhar limit why the final stage of the evolutionary path of the sun is at F. Well, because the mass of this is less than 1.4 solar masses, right? We know that the sun is around this area, so it's pretty close to the sun. So because, and remember your mass lines go something like this, and so anything around that line pretty much is going to be in this region of less than 1.4 solar masses. Okay, so anything that is in that area, of course, is then going to be too small of a mass. It's not going to be able to overcome the electron degeneracy pressure, and therefore it will be stuck at a white dwarf there at F. Okay, letter D says draw the evolutionary path of a main sequence star that has a mass of 30 solar masses, so something significantly larger, right? So something significantly larger could be anywhere as long as it's above, right? It does need to be somewhere up above. As it goes up, it should get up into this supergiant range, right? If you want to do the double thing, you can. I don't think that's super important, but as long as it gets up into this supergiant range, it's definitely more luminous than the supergiant here. And then it should come down here, and because it is going to become a white dwarf, but then it will actually go to a neutron star, which will not be as bright as anything, and so it should, and actually it should eventually, because it's 30 solar masses, chances are it's going to have enough that it's going to overcome not only the electron degeneracy pressure, but also the neutron degeneracy pressure, and it will become a black hole, which then means that it's got to have 0 luminosity, so something like that. All right, okay, that's it. You should be ready for your next set of questions. That's it.